Okay, welcome back to these sessions. In this session, we will talk about more subtle concepts about virtual functions, such as virtual destructor and slicing problems. So let's begin. If derived is a derived class of base class, then you can assign an object of type derived to a variable of type base. So derived to base, this is legal, but not the other way around. You cannot assign the base, you cannot assign an object of base type to a variable of type derived. If you consider concrete previous example, we designed discount cell and sales class in the previous sessions. Discount cell is a derived class of cell class, and because of that, you can assign an objects of the class discount cell to a variable of type cell. This is logical because discount cell is also cell, but the other way is not possible because cell does not necessarily to be a discount cell. The fact that you can assign an object of a derived class to a variable of its base class is critically important for reusing of code through inheritance and providing polymorphisms. If you look at this example, there is two class, pet and dog. Dog class inherits the pet, and pet class has a one-member variable name, and dog class has a member variable breed, and because it inherits the pet, it also has a member variable of name. And they both have a print member function, and this print member function is a virtual functions. Anything that is dog is also a pet. But the pet is not necessarily a dog. So you can assign the value of dog to pet type of variable like this. But you cannot assign the value of pet to a dog type of variable. The reverse is not possible. So vdog is a object of dog class, and vpet is a variable of pet class. And we are setting the value member variable for this vdog objects and assign this vdog object to this vpet variable. So this is legal because vdog is a derived class and vpet is a base class. So although this assignment is allowed in C++, some of the values of dog will be lost if we assign this dog object to the pet type of variable. For example, pet class does not have member variable of breed. So if we go back to this slide, pet class does not have this breed member variable. This breed member variable only exists in dog objects, not in the pet. So, and because we are assigning dog object to the pet type of variable, like this one, and because pet class does not have breed member variable, the breed value stored in the dog object will be lost. We call this as a slicing problem, because assigning a derived class object to a base class object slices of data. That is the reason why we call this slicing problem. So this is not possible. So even though vpet store the objects of dog type, and even though dog class has a breed member variable, because pet class does not have a breed member variable, this breed data is lost after this assignment. So you cannot directly access the breed using this pet class types of variable. You can argue that this is a logical consequence because object dog was moved to pet variable, so it should treat as pet and therefore not have property specific to dog. This may sound logical. Anyway, this is known as a slicing problem. Let's look at demo code for this slicing problem. So like the code shown in the slides, we have a class pet and dog class inherits the pet, and only the dog class has a member variable breed. There is no breed member variable in the pet. Dog class also has a member variable name because it inherits the pet. And they both have a member function print, which is a virtual. And the dog print member function prints the breed value, and the pet print member function prints the value of the member variable name. And in the main functions, we are declaring the pet and dog class type of variable. So we are creating the objects for the pet and the dog. And we are storing the dog objects to the variable types of pet class. So here, after this assignment, slicing problem occurs because pet does not have the member variable breed, so breed information stored in this dog object will be lost after this assignment. So if we compile this program, this program should lead to the compiler error. So as expected, compiler is complaining about this line because there's no member variable name breed in the pet, and you cannot directly access breed. Even though this pet variable stores the dog objects, because of the slicing problem, the breed data is lost here, so you cannot access the breed here. If you compile this program compiles well, and if you run this program prints the pet. So even though this pet stores the dog object, the print member functions defined in the pet class is invoked because this variable type is pet class. So you cannot even access this breed data through these print member functions. You cannot access this breed data using this print member function, and you cannot access this breed directly accessing like this way. So breed information is lost after here. This is a slicing problem. Go back to the slides. If you use pointer and dynamic variables, you can treat dog as a pet without losing his breed. For example, here we are declaring two class type of variable, pet and dog, and they are pointer. And we are creating a dog object using a new keyword. So we are dynamically allocating memory and store the dog object there. And we are setting the value of the member variable for dog object, name and breed. And we are assigning the dog object to this ppet variable, which is this one. This is a pointer variable of class type pet. So if you assign this way, this p pet variable does not lose the breed information. So no slicing problem here. But even though the breed data is not lost, you still cannot access breed data directly like this. This is illegal. Instead, you must use virtual member functions. So you have to make this print member function as a virtual and use this member function to access the breed data. So using this way, even though the ppet variable is type of pet class, the print function defined in the dog class will be invoked because ppet variable stores the objects of dog type, and because the virtual function is invoked based on a late binding that we learned in the previous session, the dog class's print function will be called, so the value of breed will be printed as well. So this is how you avoid the slicing problem. Let's look at demo code for this. So like a previous demo code, we have two class, pet and dog, and only dog class has a breed member variable, and dog class inherits the pet. So these are all same. And note that these print member functions are virtual. And here we are creating, we are declaring the class variable, pet and dog, and they are pointer types, and we are dynamically allocating the memory and create the dog types of object and store the object to this pdog variable. And we are setting the value, the member variable, name and breed for this pdog object. And we are assigning the pdog object to this ppet variable, which is class type of variable, pet class type of variable, this is a pointer variable. So this example is very similar to the previous demo code. The only difference is that it uses a pointer and it uses a dynamically allocated memory. So if we use a pointer and dynamic memory, there is no slicing problem occurs here. But even though the slicing problem is not occurred here, you cannot directly access this breed member variable like this way. This is illegal. So if we compile this program, so as expected, compiler show error message here. But we could access this breed data using this print member function, which is a virtual. And if we compile again, now as you can see here, the dog class's print member function is invoked, and the breed information, which is Great Dane, is printed through this ppet variable. So this means that ppet variable stores this breed data. That means so we avoid the slicing problems. This is possible because of the late bindings of a virtual functions that we learned in the previous session. So this is how you avoid the slicing problem. Let's go back to the slides. Let's now talk about the virtual destructor. Recall that the destructor is the special member functions which will be automatically called just before the object is destroyed. So that is the destructor. And it is good practice to always make the destructor virtual. Consider this example. Base is a base class of derived class, and derived class inherits the base class. So here we are assigning the objects of derived class to the variable of type base class. And if we delete this pointer variable, which destructor will be invoked? Thus, base classes destructor would be called because the variable type is base, or the derived classes destructor will be called because the object value that this variable holding is derived class type. Which destructor will be invoked? Think about this. The answer is that it depends on whether the destructor is virtual or not. If the destructor is virtual, then the derived classes destructor will be invoked first, and then calls the destructor for the base class automatically. And if the destructor is not virtual, then only the base classes destructor will be invoked, and not the destructor of the derived classes. So this is the reason why it is good policies to make all destructor virtual. If you do not make them virtual, some of the destructor will not be invoked. So that may lead to the memory leak. So it is always good practice to make the destructor virtual. Now let's talk about upcasting and downcasting. Downcasting is casting from parent types to child type. And upcasting is casting from child type to parent types. And usually downcasting is illegal, and upcasting is legal. So this is the class hierarchy information. Pet is a parent class of dog, and dog is a child class of pet. So this one, vpet is a pet class type of variable. So this vpet holds the objects of class type pet, and here you are trying to casting this pet type of object to the dog type of the object. So it's downcasting because pet parents to child type, casting parents type to child type, casting is a downcasting. And downcasting is illegal. C++ does not allow it. But this one is legal because it is upcasting. It's casting the dog to the pet. So it's casting the child class types to parent class type. So it's upcasting. So this is illegal. Why does C++ allow upcasting but disallowed downcasting? That is because upcasting is safe because it is simply disregarding some information like slicing problems we talked about in the previous slide. But downcasting is very dangerous because you are adding new information when you are casting it. This may lead to the security issues because it may lead to memory corruption vulnerability. So C++ does not allow downcasting. So downcasting is dangerous and therefore C++ does not allow it, but as shown in this slide, you could perform downcasting by using a dynamic cast. So pipette is an object of type pet, which is a parent class type of dog. So this one performs the downcasting, pet to dog, through this dynamic cast. So this is allowed. But I recommend that you should avoid such downcasting. If you have to perform downcasting using this dynamic cast, you must properly keep track of things so that you know the information to be added is indeed presented and not corrupt the memory, some of the memory regions. And member functions must be all virtual because dynamic cast uses the virtual function information to perform the cast. So in general, downcasting is not possible. That is illegal in C++, but you can perform downcasting by using a dynamic cast. But because downcasting is dangerous, you should avoid performing downcasting. Okay, to summarize this week's lecture, in this week we learned virtual functions. Using our virtual functions, we can provide a polymorphism. Polymorphism is a mechanism associating many meanings to one function. This means that depending on the context of your program, the same function behave differently. And we also learned new keywords, override and final. By using an override keyword, you can improve your the readability of your program, and you can prevent the programmer's mistakes. And using a final keyword, you can enforce, you can prevent derived class from overriding the virtual functions. And we also learn about the pure virtual functions. There is some cases where it is meaningless to give definitions for the virtual function. For that case, we can use a pure virtual functions. Pure virtual function does not have the definitions of the functions. And if the class has one or more pure virtual function, that class become an abstract class. And abstract class, you cannot create the objects for the abstract class. And we also talk about the slicing problem, which is about losing some data. And we talk about the virtual destructor. We saw that it is good practice to make all the destructor as a virtual, so that we can prevent some of the memory leaks. And we also talk about the upcasting and downcasting. Upcasting is safe and downcasting is dangerous, so we should avoid doing the downcasting. And in general, downcasting is not possible, but you can perform downcasting by using a dynamic cast, but it is not recommended. So that's it for this week. We have learned a lot of concepts in this week. So try to understand all these concepts because they are all important in object-oriented programming, and you need to properly know these concepts for your final exams. So study in your time, and if you have any questions, please let me know. Okay, see you in the next week.